So it's probably recording, yes. So next, we are going to start with this new chapter, chapter 4. This is about dynamics. Actually, both chapter 4 and chapter 5 is about dynamics. But chapter 5 is more like it contains some frictions and circular motion stuff and things like that. So as a result, I think within these 2 weeks, we are going to do this dynamic stuff in here. So since this is one of the important things, we will also spend some time on this. Okay. So I believe we have to spend some time on that. So I'm going to start with the basics, basically the Newton's laws of motion, the description of things and like that, all right? There are a few details that you have to know about these, but again, I urge you to read the textbook from beginning to end, this chapter and the next chapter. Only with, of course, repetition, you're going to learn some of the things. So I'm not going to say everything in here, but I'm going to say some of the things that some people have, I don't know, difficulty with. So as a result, I'm going to, I'll try to stress on these kind of details. Okay. So let me then start sharing. I think only I can share. All right. What do I share? I share this. Okay. Let me also see the. Sorry about this. I just need to do some adjustments with my Windows. I need to see the chat screen. Chat isn't here, right? Okay, and I believe you can open your microphone at any time, and you can also ask a voice question. I don't know what KVKK says about this recording the voice, but in any case, just keep this in mind. All right, so let's start with the Newton's laws of motion. So this is the first law that we are going to see, essentially. We have talked about this gravity thing before. So, I mean, that's basically, we are going to talk about what law is in a moment, but let's just summarize this. So we have seen the kinematics part before. That's basically the study of the motion by itself. So we have this reference frame, and then relative to that reference frame, we have defined the concepts of position, velocity, and acceleration, and things like that. So it was just that. It was just mathematics, actually. So there was nothing in there. But now we are going to relate the motion to the physical concept. And so we will basically be dealing with this force concept and its relationship with the motion. And that's basically what dynamics is. So how does the force affect the motion, basically, right? It is a law of nature. It's not a law of mathematics. So essentially, this means that this is actually a non-trivial statement that you cannot find by thought alone. It's not the thing like the kinematics, for example. In the case of kinematics, you can define things you just need the mathematics in there, and you just need the correct mathematics. Here, however, I mean, there's some kind of a statement in here. These are the laws of the motion. I mean, in principle, the statement might be something else. I mean, the laws of the motion could be something else. So as a result, we cannot find the correct laws with thinking alone. And that's how perhaps the Greeks actually couldn't find the laws of motion, basically, or I mean, the science didn't start at that time because they were thinking that they can actually find everything with pure thought alone, right? So in any case, with Galileo, we have this experimental procedure. So whatever we are thinking, we are basically thinking by just looking at the nature itself. So sometimes, if it is necessary, we are also doing the experiment. And from all of these, we somehow combine all of this knowledge. And then at some point, somebody comes, like Newton, and just summarizes these with a few statements. So these are the laws. So at this point, we are just going to accept these as they are. We are not going to question them. So we are just going to see the implications. So by saying that we don't question them, of course, I mean that we are not going to question them within that course, but obviously as scientists, we have to question everything. So we know that the Newton's laws of motion are not actually God-given. We know that they are wrong, for example, from the modern physics perspective. But in any case, from within that course, so we are going to just accept these as it is. So that's basically our starting point. And from the starting point, we are going to deduce the other things like, I don't know. So we are going to deduce the concepts of, for example, energy and things like that, right? So most of the concepts that we use in physics has a basis in this, in the laws of motion. And so as a result, for that reason, this is also important. But again, I mean, we know that these are not entirely correct. So there's this relativity and quantum mechanics and things like that. There actually just does some modifications in there. But somehow it is also fundamental. So by using this, we actually defined all the other concepts that we use in physics. So again, this is the dynamics part. And of course, probably I should start with what is the force concept. I have actually asked this question before in the first hour, actually. I have said that it's essentially, let me just repeat this, it's just some aspect of the interaction of two objects. So let's see it like this. Physical objects interact with each other, right? Interact with each other. So there's something called interaction. This can be in many different ways. So for example, this might be a magnet, and well, this might be another magnet. So therefore, they somehow interact through this magnetic field with each other. In any case, there are possibly all different kinds of interaction as well. But there's this aspect of the interaction that changes the kinematic state of the objects, right? And somehow force is the concept that is relevant to that aspect of the interaction, right? Probably this is the best way that we can define this force concept. Unfortunately, I mean, before this point, we don't know anything about physics, right? This is the first law that we are going to define. And in the first law that we are going to define, we have to define this concept of force, but there is nothing that we can actually define it with, right? We don't know anything at this point. So as a result, there is no way for us to precisely define what force is. We can only define it in the scientific sense, only after we see the second law of Newton's second law, basically. In that case, of course, we see how the force somehow enters into the equations. So only with that we can define it. So there's some kind of a circularity in here. Unfortunately, at the very first point, we need to have something like that. Okay. So in any case, there's an interaction in here. So we somehow forces the quantity that quantifies that interaction. So as a result, if this interaction is strong, then in that case, the force is strong. So that's one thing. And if there is no interaction, then the force is zero. We can say that. There's another thing. two objects interact with each other. We don't have a single object interacting with itself, so that concept is not defined. And the force is somehow affects both of them. So as a result, somehow this interaction affects the other one. So if two objects are interacting, then both of them are influenced by each other. So that's essentially Newton's third law. That's basically that statement. But if we think of it like as some kind of an interaction, that's probably the best way of thinking about it. So that's also true for any kind of interaction between two objects. So if somehow this object influences something of the other object, then it's also the vice versa as well. Okay, so there's some kind of a generalized version of this third law. But in here, of course, we are going to state the third law with this in mind. So let me, it's just like 20 minutes past already. So let's start with this Newton's first law. It's also called the law of inertia. So it just defines the concept of inertia. So it basically says that if there is no force acting on an object, then it says that if it is at rest, it will remain at rest. And if it is moving, then it will keep moving with the same speed along the same direction or something like that. So in any case, you know this, so I'm not going to say too much about this, but let's just say that, all right, this is too wordy. Probably Newton at the time expressed it like that. I don't know how he expressed this precisely, but probably it was something like that. But since then, we have defined new mathematical concepts and things like that. We just say that, well, we don't talk about the speed anymore. We talk about the velocity. So as a result, instead of doing this, we just say that the velocity is constant, right? So if it is at rest, the velocity is zero. So it's just constant, meaning that it will remain at rest. And if to say that it's moving along the same direction, we don't form a separate statement. We just say that the velocity is constant, right? So since the velocity is a vector, by constant, we mean that it has the same direction and same magnitude. Okay. So sometimes, instead of saying that there is no force acting on the object, they sometimes say that the net force is zero, right? I mean, if there are forces on the object, like, right, if the net force on object is zero, sometimes I'm going to use this version, sometimes I'm going to use the other version. It doesn't matter, actually. So this is essentially a special case of the second law, but historically it was important. We have talked about the Aristotle. He was the first one to talk about the, no, he was not the first one, I believe. But in any case, he's the first one who talked about everything, actually. Everything in nature and in metaphysics and things like that. So he has a book about nature, physics. And in there, of course, it was Aristotle's statement that if there is no force, in that case, there is no motion. So the object will, let's say it like this, every object will stop. So Aristotle thought that, of course, the natural state of every object is the state where they will stop. So as a result, if there is no force to maintain motion, in that case, it will just come to a stop, right? In any case, this was just this ancient knowledge obtained by pure thought. But starting with Galileo, of course, Galileo objected to many things said by Aristotle, and it's basically the law of inertia. So Galileo also reasoned with his reason, but he just deduced that if an object is moving and no force is acting on it, then it should keep moving. So somehow he was able to deduce, again, by thinking, but of course, this thinking is based on some observation as well. He just deduced that this inertia thing is basically um, is a law of nature. So let's say it like that. So if an object is like that, if it is moving with some velocity and there's no force on it, so it will basically keep moving with the same velocity. So as a result, a force is needed to change the velocity. So therefore, a force is needed. In that case, the velocity, if there's a force, then the velocity would change. So that means there should be an acceleration. So the acceleration would be non-zero. So from here, we can then deduce that the forces somehow should be related with the acceleration. And just keep in mind that velocity changes if either its direction or its magnitude changes. Again, let's just keep it short. So as a result, the first law of motion says that if there's no force on an object, then its velocity is constant. All right, then there's this next question in here. I don't have any. Yeah, sorry about this. I speak, but I don't hear. So the third law was not valid for me. So if I speak, then I should also be able to hear, right? Sorry about this. I hope that I'm not muted, right? So everything seems okay. Okay. So in any case, velocity is constant. But we have said that the velocity is a relative concept. So in different reference frames, velocity is different. Sometimes the accelerations are different. And so perhaps in that case, the concept of, velocity being constant may not be the same in all reference frames. Okay? So as a result, it is not possible that this statement is valid. Sorry about that. This whole statement is valid in all possible reference frames. So no force means object is not interacting with anything. And this is not something relative, right? If an object is not interacting, it's not interacting relative to any reference frame. So that's some concept which is independent of the reference frame. And so as a result, the conclusion that we have stated in here can only be valid in some certain particular reference frames, okay? So as a result, this is not valid in all reference frames. So this also implies that we have to use reference frames where this is valid. So I'm just going to define this. So I'm going to add a page in here. So we just call these as inertial reference frame. Sorry about that, reference frame. I just defined this as a reference frame in which the law of inertia is satisfied. All right, so and I'm going to talk about this. So what are the inertial reference frames? Can there be more than one inertial reference frame? So obviously, yes, any reference frame where the velocity of an object for which there is no force acting on it is constant should be an inertial reference frame. So from here, we will deduce that if a reference frame is moving with constant velocity relative to an inertial reference frame, then that's also an inertial reference frame as well. But as I said, I'm going to talk about reference frames later. But here, we just need to keep in mind that the laws of motion or the laws of physics cannot be valid in all reference frames. They are valid only in inertial reference frames. So let's just say it like this. All laws of physics are valid only in inertial reference frames. So the first law is an example of a law of physics that's valid only in inertial reference frames. And we are going to see that the second law is also. But there are some other laws as well that I'm not going to mention, like I don't know, the law of, for example, the motion of the light rays, for example, and things like that. These are only valid in inertial reference frames. So most of the laws of physics, we just formulate them in inertial reference frames. So as a result, we have to think about whether we should use some non-inertial reference frames in describing physics or not. So as I said, this is something else. I'm going to talk about this. I'll talk about it later, but not right now. So then the second law, right? That basically says that the net force acting on, well, we have just said that there has to be a force to change the velocity, so therefore there has to be an acceleration. It basically says that the acceleration is proportional to the vector sum of all of the forces. So as I have said, this is how we define the force concept. So as a result, there are some things that are defined in here. And the mass concept is also, this is a physical concept, right? This is the first time that we are using the concept of mass. So as a result, this is also defined through that equation, okay? So there are many things in here, but let's just talk about the net force in here. So that's the net force. So that's basically the vector sum of many forces. So first we are saying that the force is a vector quantity in here. And then second, we are saying that if many forces are acting on an object like this, in that case, we have to add them up vectorially. So there's this vector sum of all of these three forces in here, for example. Yeah, I couldn't translate them. So somehow we have to move them in space, and so that I just connect them tip to toe. And then the net force is just the vector sum in here, okay? So we can either do it like that and compute the net force like this if we have these arrows, or we just use this unit vector notation. So we know that the net force has an x component, which is the sum of the x components of all of these forces, okay? Just keep this in mind. So we can do the same thing for the y components as well, but let me not write these kind of things in here, okay? So that's the first thing in here. A lot of students might also get confused about this, but I need to state this in any case. So we add up the vector, the forces, all right? So the forces might be in different kinds. So there might be different forces acting on an object. So as a result, we have to add them up. But we don't have different accelerations on an object, okay? So we don't have anything like, I don't know, acceleration due to force 1 or acceleration due to force 2. We just have a single acceleration because this is a kinematic concept. Because we defined acceleration through the motion of the object, and the motion is just a single motion. Just keep this in mind, all right? Sometimes there are also people who just ask these kind of things like, what's the acceleration due to that force and things like that. Well, no, we just talk about the net force and the acceleration due to the net force, actually. Another thing, so mass. Mass also enters in here. So in here is basically a measure of inertia. So inertia is basically, think of it like that. It is the resistance to change the velocity, right? You can think of it like that. So it's like the unwillingness of an object. But of course, the objects do not have any wishes or wills or, I don't know, thoughts, things like that. So as a result, it's not correct to personalize objects. But in any case, it just somehow has some kind of a resistance to the change in the velocity. And so therefore, mass is some kind of a measure of it. So from the second law of motion, when you apply a certain force, I have to divide the force by the mass to get the acceleration. So that means bigger the mass, smaller the acceleration. So therefore, that means the bigger the resistance to the change in the velocity, right? So as a result, you can think that the mass is a measure of inertia. So that's the best way of describing the mass. But I know that in high school, you just learn or I don't know, perhaps in secondary school, mass is a measure of the amount of matter. Well, that's not the definition, right? Let me just say it like that. So mass can also be taken as a measure of the amount of the matter, but that's not the definition. So there might be some situations like, I don't know, matter might have some extra energy, and because of this, its mass might be bigger and things like that. So it's the same amount of matter, but somehow the mass is larger. There are these kind of situations that we mean. So by this, we mean that the inertia of the object is bigger. I mean, if the mass of the object is bigger, then that means the inertia is bigger. So we will always keep this definition in mind. So for us, mass means is the measure of inertia. So mass is basically, at this point, is just the quantity that appears in the second law of motion. So we don't have any other definition. Later, we are going to see that mass also enters into another law of nature. It's the Newton's law of gravity. When time comes, I'm going to talk about this. So there's a subtle issue in there, but I'll talk about that, okay? Just keep this in mind. Let's talk about this force unit as well. I'm also forgetting about this. So we just defined the force concept through that equation. So as a result, to measure the magnitude of a, I don't know, force, somehow we have to use this thing, and at least at the first steps. And then once we have some kind of a way of measuring some certain force, and perhaps we can measure other forces based on this as well. But in any case, we have to define this. So therefore, the unit is as well. So the unit of the force basically should be in SI, kilogram meters per second squared. And of course, we just call this as a Newton and show it with the capital N symbol. Right, there's a strange convention in SI that says that if a unit is named after a person, then the shortened form should be capitalized. So this is always a capital N, but the long name of the unit should not be capitalized, because this is not the name of the person. When you're saying that the force is 2 newtons, you're not imagining that it's the Isaac Newton in there. Is something else. So this is the name of the unit actually. So as a result, somehow they just suggested that this long name should actually start with a small letter, right? Just keep this in mind. This is just a convention that people use. To that convention for the capitalized form of the shortened form, liter is an exemption. So they used to write the liter with a small l, but somehow, I mean, people just confuse this a lot. So as a result, they just adopted this exception. So liter is not named after a person, but we just write its shortened form with a capital L, and that's the only exception. So for all other units, if it is named after a person, it's always capitalized, okay? Just keep this in mind. So that's one of the things that we are going to use. And then we have the third law. So that's the sometimes called the action-reaction principle. This is something that, I don't know, it's usually forgotten by most of the students, but that's one of the important things in many respects. So let's remember that this is an interaction. Again, two objects are interacting with each other. So every force is applied by some other object, right? So as a result, we have two objects in here, A and B, two objects. So if a force is applied on B, then it's applied by by A. So I usually show it like that. So I just put a point on the object of B when I'm talking about the force applied on B. But this is applied by A. So therefore, it's a force on object B, but applied by A, right? And sometimes I'm going to use this notation for that. So that's force on B applied by A. But I mean, whenever I use this notation, I'm going to explain. So in that case, it says that there's also a second force on, this time on the other object, force applied on, sorry about that, force applied on A, but it is equal and opposite to that force. So therefore, this is the force applied on A by B this time. It's just equal and opposite. So as we have said, this is basically because of the fact that they interact and the interaction affects both objects. And somehow this force quantity should be the same for both objects. Again, we don't question them, and that's one of the things that we cannot deduce by thinking alone. But later we are going to see that this is an extremely crucial law for the conservation of linear momentum and conservation of angular momentum as well. So in the case of conservation of angular momentum, I'm going to come back and then say that there's some missing detail in here, all right? Some people just call this as the action-reaction principle. And so they think that this one of them is an action, so the other one is produced because of this, there's an action in there. Don't think of it like that, right? So some people just think this as a cause-effect thing. So they think that first one of the forces applied, and after this is applied, the second force arises. No, that's not the case. Both of the forces are present at the same time, right? So because of this interaction thing in here, so whether there's an interaction or not, that's basically the question. So as long as there's an interaction, there's a force, and both forces will be present at the same time, all right? So that's not something that we choose. So sometimes you push on the wall. Of course, you just choose to push. So as a result, you can think yourself as the cause of the force. Well, there's no difference between the cause and effect in here. So there's a force applied because somehow your hand becomes very close to the wall. And so as a result, the electrons in your hand and the electrons on the wall start interacting with each other. So they never actually think about there's some kind of an intent to apply a force in there, right? So as a result, just don't think of it in terms of like one is the action and the other one is the reaction. No, there's no such order in here. So you can equivalently state that the other one is the action and the first one is the reaction. Okay, so I'm going to state it like that. This is the notation. So force applied on A by B is equal to the negative of the force applied by B on A. So I'm using, again, vector calculation in here. So these two vectors are equal in magnitude, but opposite in direction. Okay, so that's, from time to time, we are going to use this, but I mean, we don't actually use in all problems, but just keep in mind that there's this thing in here. So let's start with some forces. The first force that we are going to start with is the gravitational force. In that case, we are just going to start with this observation. And we have said this. So any object in free fall is moving with acceleration equal to the gravity. So the acceleration is equal to the gravity in here. And so therefore, the net force acting on this object is basically has to be equal to mass times that acceleration. So therefore, this force is the gravitational force. Let me just do it like that, right? So the net force is therefore, because of the second law, this has to be so. Therefore, there has to be a net force acting on that object that's equal to mass times the gravity. And we just call this as the gravitational force. Basically applied by the Earth. Okay, so we just call this as the weight force. And this is the weight force, let's say, on the object. But sometimes we just call it as the weight of the object. I'm sorry. Object, okay. So I'm going to show it with a capital W sign, at least in here. So it's equal to mass times gravity. In all of these cases, I'm going to show this with a vector sign. So by weight, of course, I'm going to mean the vector thing in here. And so as a result, yeah, let's just keep it in here. So when time comes, I can therefore say something about this. So of course, there's also a scalar quantity, which is just the magnitude. So that's equal to the mass times the gravity. So that's the first applied, that's the first force that we are going to say that exists. So therefore, we are saying that Earth is applying this force on the object. Let's say the object is in free fall, or I don't know, the object might also be resting on the Earth, or I don't know, running on the Earth, doesn't matter. The Earth doesn't care whether you are in free fall or not. So it applies the same force all the time. And because of the third law, therefore, this object should also be pulling the Earth towards itself. So that's basically an attractive force. And we just think that, of course, this force is applied at the center. So we are going to talk about the point of application. So therefore, there's an equal amount of force applied on the Earth by the object, okay? So as a result, the object and the Earth are they are pulling each other towards themselves. So of course, this is something that we don't directly experience, but this is the case. So there's also this action-reaction thing in here. So the reason why we don't usually think about this is that the Earth is huge and this force is small. So as a result of that small force, the acceleration of the Earth is extremely tiny. If you want, we can calculate this actually. But this is basically negligible all the time. So as a result, we never need this, but we should know that, we should keep in mind that this force is there. That's important. All right, I'm speaking a lot actually. So then let's talk about this contact forces. Every force that we are going to see, excepting this weight force, is basically an electromagnetic force. This is essentially the force between the electrons and protons inside the atom, essentially. So when two objects are in contact with each other, there's essentially force applied by these electrons to each other. Sometimes these forces might be attractive because of the attractive force between electrons and protons. Sometimes it's repulsive. In any case, when these two objects are in contact, we know that there are these two forces acting on these objects. So there is a force applied on this object. So I'm just going to call this as the contact force. And of course, we know that there's an equal and opposite amount of force applied on the other one. So that's minus F contact in here. So both forces act on, well, two forces act on these two objects. So they are not, we don't say they are the same force. They are different forces, but both of them are present. Right, there is a convention in here, and we are just going to follow this convention. We just, there's some kind of a plane of contact in here. So there's a surface of contact. So usually we think of this surface as some kind of a plane. So that's a surface of contact. All right. And then I'm going to do it like, I think I'm going to use the white color in here. We basically think about these two parts of the force. One part which is perpendicular to the surface, and we call this as the normal force, and one part which is parallel to the surface, and we just call as the friction force. All right, that's basically the definition. So whenever we say friction, this is essentially the parallel component of the contact force, right? Let me just say it like that. N is It's not the component because we think of this as a vector. So let's say it like this. I'm going to say part of contact force perpendicular to the surface. Perpendicular, the word normal is actually another word we use for perpendicular to the contact surface. Okay, and then the frictional force is parallel part of contact force. Okay, so as a result, I mean, these two forces are actually as a result of the same mechanism. It's the same electrons that are interacting with each other. But somehow, because you would like to think that there's some kind of a surface of contact, we just mentally separate these forces into these two components, right? Just keep this in mind. So most of the time, both forces are present in there. All right, so I spent a lot of time describing what forces are and things like that. But of course, we have to understand all of these forces. So some of the forces have this nature of being a constraint. I'm going to talk about this after we have the break, all right? So let's have a break. After the break, I'm going to talk about these forces, and then I'll start talking about, I think, this normal force, the tension force, and the just these, right? Normal and the tension forces. So let's have a break with this on screen. All right, we will meet at 45 past. Uh, 10:45. Okay, have a nice break. All right, we are back. Welcome back. So we have been talking about the constraints. Constraint is basically a restriction on the motion. So because of some physical restriction, an object cannot move in an arbitrary way. So for example, the book on the table, so the book can actually move horizontally, or it can move vertically up basically, but it cannot go down because somehow well, the table is there, obviously. So the table somehow prevents the motion of the object. And so as a result, I mean, if you are pushing I don't know, if you just place the book on the table, somehow there has to be a force associated that somehow appears that prevents the book going into the table, right? So basically for every constraint, since these are physical constraints, there should be some kind of a contact force actually that satisfies that restriction in a way. So this is perhaps a mathematical way of thinking about it. So we think of constraints mathematically, but there's also an associated constraint force, all right? So in the special case of the book on the table, it's the normal force. So there's a normal force in here. So we are going to see this force a lot, but just keep in mind that this is a special constraint force. So it's basically there to prevent the object going inside the other object, right? So it's always present in contacts, of course. So the strings also do the same kind of a job, essentially. When it is tight, the distance between 2 points, 2 ends of the string is fixed. That's constant. It doesn't change with time. And so therefore, this is also a constraint. And in that case, the tension on the string is a constraint force. I'm going to talk more about this. And then there's this case where, for example, when an object is on a surface, of course, there's a normal force that prevents the object from going inside. But there are some cases where it doesn't even slide, for example, slide on the surface. So even that motion is prevented. In that case, for example, we are going to see that there is this something called the static friction force that actually does this. All right, so we will actually talk about each of these forces separately, but just keep in mind that these are just special cases of constraint forces, the normal force, the tension force, and the static friction force. The problem with these forces is that, did I write this thing down? Yeah, there's a constraint and a corresponding constraint force. The problem with these kind of forces is that, it's not a problem, it's somewhat a trouble actually. The amount of the force somehow is adjusted to an exact level so that this constraint condition is satisfied, right? So I don't know, let's just think about it like this, have an object on the table, for example. If the table applies a too large force, let's say it like this, I mean, this constraint force is bigger than the weight force, let's say, at least for a moment. In that case, we know that there will be some kind of an imbalance of forces acting on the object. So therefore, this object is going to accelerate downward, right? So that means in here, for example, I think I need to have some kind of a magnification of that region in here, right? I can magnify that region. So there are basically some electrons in there that belong to the object and some electrons that belong to the table. They are actually applying these forces to each other, right? They are pushing away each other. And when the object is lifted up slightly, the distance between these electrons increases by a very significant amount, in which case this force is going to basically become smaller in magnitude. So as a result, by a very small motion, I mean, you don't even notice that motion. By a small motion, this normal force basically just decreases. And let's say that if it decreases below the weight, in which case, of course, the opposite happens. So this somehow, there's a mechanism in here which basically increases that normal force whenever it is smaller than it is necessary, and decreases when it is bigger than it is necessary. So eventually, you're going to reach to a situation where this normal force is exactly equal to the value that it should normally have that satisfies that constraint condition, okay? But since we don't see this motion in here, and this basically happens very quickly most of the time, the time scale is very short. So as a result, we don't actually notice its presence. But in all of these problems, it just appears that, I mean, somehow we have to compute the value of that force, but somehow by just looking at the picture, we cannot understand this value. So somehow we have to solve the whole problem, apply this constraint condition, and only after that you can find this value. So in here too, it just appears that in that case, the normal force, the constraint force is equal to the weight force, but I can only decide this after solving the problem. Okay, that's one of the subtle issues in there. Just keep in mind, that the normal force, the tension force, and the static friction force, for these three forces, this is the situation. And from time to time, I'm going to remind you this. We will talk about some complicated constraints later, but for now, we are just going to talk about some simple cases, okay? So the tension, so we know what the normal force is. Let's talk about the tension. So the tension in a string, basically, we are talking about this. So in that case, again, I'm just going to do some kind of a magnification in here. So this is the magnified picture in here, all right? So in that case, the string is basically a very thick object. It's not thin, all right? And there are some atoms in there, and these atoms are tied to each other, connected to each other by a chemical bond. And this chemical bond is the one that actually supplies a force. There are actually forces between all atoms, but normally what we do is we just mentally divide that string into these two parts. So let me say it like this: mentally divide string into two parts. And then we talk about the atoms that lie on one side and the atoms that lie on the other side. They are still connected with a chemical bond, and so therefore they are applying forces to each other. So they are attracting each other, right? And the tension force is essentially the total force that we observe that's applied between these atoms. Okay, again, this is something microscopic, and its value can change significantly by a very small change in the distance between the atoms. So as a result, it can increase a lot by a very small change. So therefore, when you make a string tight, you don't actually see a change in the length. But when you increase the tension, it appears that the length didn't change, but the atoms actually experience a significant change in length. And so therefore, the tension changes. So let me just do it like this. The upper part applies this force to the lower part, and the lower part applies this force to the upper part, basically. So these two parts are pulling each other, attracting each other with a force which is parallel to the direction. And since we can find the direction easily, we usually quote the value of the tension, right? So as a result, we always write the tension as a scalar. So this is a scalar quantity, but by using the scalar quantity, we can determine the vector force. So don't get confused by this, all right? The tension is really a tension force is really a force, so therefore it's a vector. But to find the tension, we use this, to find the force, we use this quantity as the scalar quantity. We just treat this as a scalar quantity, and we use the scalar value to find the vector, right? I know that some of you are still confused about this vector concepts, but keep in mind that, I mean, whenever I write the tension, I always write it as a scalar value, and most of the time we deal with scalars at the end, of course. So this is just an example used to illustrate a concept, basically. So we have a 2 kilogram mass, which is tied with a string, perhaps a chain, basically, which also has a mass. It is 1 kilograms, and we are asked to find the value of the tension. Let me write TA in here. In part A at the lowest point, and part B at the midpoint, and part C at the topmost point. Okay, so this is one example of what I have been mentioning about by the constraint force. The amount of the tension in the string is basically the amount of the force that develops. That satisfies that condition. The condition is that this mass is hanging there, it's not moving. And somehow, the tension value should be adjusted so that this satisfies that condition in here. So I'm not going to do much in here, but I'm just going to write down the results, but let me just do it like that. Let me do the part B in here. I just do this mental division in here. I just divide the string from this midpoint into 2 parts. So as a result, I'm going to treat this as the object in here. So I have basically a 0.5 kilogram portion of the string in here and 2 kilogram portion of the block. And so as a result, this is the combined object. Okay. And what do I do? Well, I basically write down all the forces. So as a result, there's a weight force in here, which is basically equal to, in magnitude, that's 2.5 kilograms multiplied with, let me write it down like that, right? The total mass times the gravity. And then there's this, yeah, that's yellow also. The upper part of the string applies a force on the lower part of the string, which is equal to TB, and that's the force applied by it. Right? So there are some other forces in here. We are going to call them as internal forces. So as a result, later we are going to see that they are insignificant, but at this point I'm just going to say this. So we don't need to include internal forces. Internal forces are forces like the forces between atoms and things like that, and the force between this string and this block in here, whatever. Since I have said that this is just a combined object, any force that acts within that combined object is an internal force. So when we are drawing these free body diagrams, we don't include them into our calculations. Just keep this in mind. We are going to see the reason why later. But in all of these calculations, of course, these kind of forces, even though they are present there, they don't enter into the calculation in here. So in any case, in this situation, I'm just going to cut the story short. We basically write down the Newton's second law like that. It's the mass times the acceleration, but the acceleration is 0. So therefore, from here, we just deduce that these two forces should be equal to each other. Okay. So as a result, I'm just going to write down the result in here. The TB should be equal to basically 2.5 kilograms multiplied with the gravity, which is 10 meters per second squared. So therefore, this is 25 newtons. But I'll just quickly say that I can do the same calculation for TA and TC as well. So TA is 20 newtons and TC is 30 newtons and TB is 25 newtons. Okay, so that's the result basically. So essentially, therefore, the tension on the string depends on where you are computing it, because that's basically tension is the total force between the atoms, at that region. And we have different atoms at different regions, right? Obviously. Okay, but you can see that the fact that the tension depends on the location is actually related with the fact that the string has a mass, okay? I mean, if the string did not have a mass, then we wouldn't have this. And that's basically the conclusion that we should have in here, right? Basically, I'm going to say that if the string is massless, in that case, the tension has the same value on every part of the, at least on every straight part of the string. So you can easily deduce this. You can consider this thing as an object. Sorry about that. Right? Isolate, just consider these 2 points and isolate that part of the string and consider that part as some kind of an object like that, right? Something like this. And then you will notice that this part is pulled with a force which is equal to T1, and this part is pulled with a force equal to T2. And then you're going to notice that the T1 minus T2 is equal to, it's the mass of the string multiplied with its acceleration, but the mass is 0. So therefore the tensions should be the same. In any case, I mean, this is basically what we say. So if the string is massless, then we can safely say that the tension is the same everywhere. There's another thing in here. If there are in some cases, we will talk about pulleys. I will start using them. At first, we are going to assume that they are massless. And later, we will see the case, what happens when they have mass. So at the end, this is what I'm going to say in here. So this is just accept this, but keep in mind that we are going to show this later. If a single massless string goes around massless pulleys, then the tensions in different straight parts of the string should be the same. So therefore, these 3 tensions, for example, T1, T2, and T3, must be equal to each other. Only if the strings are massless, we will see the reason why later, right? So for now, we just accept this. So that means massless strings, massless pulleys, then we can say that, safely say that the tension has the same value everywhere. There are situations where we have 2 different strings tied like that, for example, in which case there's no reason why the tensions in these 2 strings should be the same. So just keep this in mind, right? All right, so I think I'm going to, I still have time. So let's just start with some problems. So let's just start with the sample problem. I have a hand in here. I don't know how to show my hand. I can draw my hand like that. I don't know. So I'm pulling this string upward with a force F. And I would like to know if what should be the force if I want to move this load in here, which is 1 kilograms. If I want to move it up with constant speed, and in part B, if I want to lower it down with constant speed, and finally, I'm going to look at this case where what happens if the string is I'm pulling the string with a force of 15 newtons. Again, I mean, this is just a problem where I'm introducing some of the concepts, right? You can think of it like that. It's a very simple problem, actually, but some people might still get confused about these kind of things. So let's start with this. The force between the hand and the string, right? So let me add a page. Let me draw this hand again. So that's my hand, and that's the string. So we are applying a force on each other. So again, I just divide this into these 2 parts, right? So there are these 2 objects. The object A, let me write it down like that. There's this object hand, let's say. Let me call this as H. And this is the object string. So with this division, of course, there is part of the string which I also included as part of the hand. No problem with this, right? I can always think that, right? Just keep this in mind. I mean, mentally, analyzing this thing might be very complicated if you don't do these kind of tricks. So as a result, I'm just going to assume that the string somehow starts from some point in here, and the rest is basically hands. So in that situation, you can see that the force is applied by the hand on this lower portion of the string. So therefore, this is basically upward. So that's the force F in here, which means the string is applying the force, which is an equal amount of force to the hand. So the string is pulling the hand downward. And I can also think of it as basically the force applied by the string on the part of the string that remains in the hand part, right? Something like that. So therefore, this is equal to the tension. So that means tension is equal to the force applied by the hand. Sorry, that's in magnitude applied by the hand. Let's say it like that. This is in magnitude, because in direction, of course, they are opposite. So this is basically Newton's third law. But in magnitude, I can say this, that the tension is the same thing as the force applied by the hand. So that basically clarifies this. So whenever I say I'm pulling the string with a force of 15 newtons, I'm essentially saying that this is the amount of the tension in the string. So in that case, therefore, let me use the yellow color in here. We have tension equal to T on both sides of the string, because it's the same string. And then we have this isolated object in here. I'm going to include the pulley inside the object. All right. Let's see it like that. I'm going to add a page also in here. So we have this thing in here, and this is my combined object, all right? Mass is basically mass plus the mass of the pulley plus mass of the strings, but they are massless. So therefore, the mass in that case of the combined object is still m. And then we just then show the forces acting on these. So again, I need to compute only the external forces. So the outside objects apply some forces to this combined object, and I have to include them all. So you can see that the Earth applies this weight force. So that's by Earth. This force, this T, is applied by string on right. And there's another tension in here which is applied by string on left. All right. Yeah, there are these two parts in here. So when I do this mental division, both the part on the left and part on the right, they apply a force. So as a result, and then we have the Newton's second law. So let's say that the acceleration in the upward direction is equal to a. I'm going to explain the meaning of these kind of symbols later, but let me just quickly continue in here. So 2t minus mg. I'm also going to explain why I'm putting minus sign in here, right? It is mass times acceleration, so that's basically Newton's second law. In this part A, basically we have acceleration is equal to 0. So that's part A. And so as a result, the tension should be equal to 1/2 of the weight of the object. And in this case, this is 5 newtons. So in all of these cases, I'm going to take the gravity always as 10 meters per second squared, right? Always, let's say. The reason why is that I don't want to just spend time with just computing, multiplying numbers, right? That's the only reason. Otherwise, I mean, if you have time, you should take the better known value. So in any case, so there's no difference between part A and part B. Let me add this. The tension is equal to 5 Newton again, same. So that means that in order to lift the object up or lower it down, your hand should apply the same force. So this is basically also equal to the force applied by the hand. Why is the mass times acceleration is equal to 0? There are different reasons. So if the mass is 0, that's also 0. If the acceleration is 0, that's also 0. I don't know what you're referring to. So at least for that problem, the acceleration is 0 because I said that in the problem I have said this, that it's moving with constant speed in the upward direction. So that means constant velocity, and so therefore the acceleration is 0. In part A and B, basically we have 0 acceleration. Let me continue with this. I'm too far behind. Sorry about that. All right. So what's the difference between A and B? I think this is a conceptual question. I mean, when you want to lower this object, you are going to do something, and when you are going to lift it up, you are going to do something else. But this problem says that in both cases, the force applied by the hand should be the same. It is 5 newtons in the upwards direction. So what's the difference then? Why there is a different motion here? I'm not going to answer this. I just want you to think about it, right? In part C, we have this. In that case, the force applied by the hand. So somehow I adjusted my hand in such a way that my hand applies a 15 Newton force. That's basically equal to the tension. So it's the same equation again. It's the 2 tension minus mg that's equal to mass times the acceleration. But this time the acceleration is not 0. So we have 2 times 15 in here. Mass times gravity, that's equal to 10. So that's equal to the acceleration. And so therefore the acceleration is equal to 20 meters per second squared. In here. All right, so that's basically what it is. So again, there's a 2t in here because it's not just my hand that is pulling the object up. It is these 2 strings which are pulling it up, right? Somehow we can apply these 2 forces. All right, so let me then talk about this. I have 15 minutes. So if an object has mass equal to 0, well, this is just an idealization, obviously. So none of the objects have 0 mass, but it means negligible compared to the other things. So as a result, within this approximation, this is true. Then the net force on the object is 0, no matter how the object is moving or accelerating, right? So that's one example. For example, I don't know, I have this kind of a thing, perhaps. I don't know. Let's say that we have a rocket. We have built this rocket by ourselves, and then There's a ceiling in there and then a wall in here. And there are these strings are attached and there's a hanging mass like that, all right? Suppose that we have this kind of a system in there. Yeah, in any case, so perhaps the rocket is accelerating. So therefore, these systems are also accelerating. Okay, in any case, it is this problem. I know that some of you have solved these kind of problems a lot in the past, so as a result, I'm not going to solve it. So as a result, there are these three strings that are tied together. So if I just call these tensions in here as T1, T2, and T3, then the corresponding forces should be equal to 0. Right? The reason is that you can think of all of these three tensions applied to a point at the connection point. So this is an object with mass 0. It's not there, basically. And so therefore, I'm going to erase this picture in here. Sorry, forget about this rocket thing. It's not that important. So therefore, this is what we are going to do. And in that case, if you just consider these three forces, this T1, T2, and T3. So this time I'm just going to draw them as vectors. So we should have like the T1 plus T2 plus T3 should be equal to 0. Why? Because normally this is equal to mass times the acceleration. Acceleration is non-zero, but the mass is 0. And so therefore the right-hand side is 0. So since this is 0, even though acceleration is non-zero, the right-hand side would be 0. So however it accelerates, doesn't matter. The total force on it is equal to 0. But of course, in reality, we know that the total mass is non-zero, but it is negligible. So that essentially means that the total force on it has a negligible value. But in most of the idealizations, we just take this to be equal to 0. So that's correct, the last comment, yes. So it's basically the initial condition. So, but after the object has this reached to that final velocity, after that, we just keep the force to be the same. T3 cannot be negative, all right? The tension can never be negative. Tension is always positive thing, so it's that positive value. I mean, when you have a loose string, the tension becomes 0. If it is a tight string, then the tension is always positive, okay? So, but this, sorry about that. The force in here, this T3 vector force that I have shown in here, right? This is a vector, but the sign has nothing to do with this. Which mass are you talking about, Sinan Ergün? In any case, in this case, I just talked about the point of connection in here, or you can just take some part of the strings as well. It doesn't matter. I mean, since the strings are massless, when you just think of this as an isolated object, it is an object with mass 0, so therefore the total force on it should be 0.
I implied the teacher, we built the mass at the bottom of it, T3.
Yes.
We don't calculate it.
What?
The M is, what does that mean? Mass of the...
Yeah, mass of the object, yes.
Yeah, object, yeah. Do we calculate it?
No, I'm not going to solve this problem. I'm just illustrating the principle. But yeah, I mean, if you want, you can also solve the problem as well. I said that, however, this is moving. I mean, I said that this is inside the rocket, so therefore this is accelerating upward. So this point, the ceiling, and as well as the mass has some kind of an acceleration. But independent of what the acceleration is, I said that the total force acting on this joint in here, joint on that picture, that has to be equal to 0. And the reason is that that joint has 0 mass, right? That's what I have said.
Oh, okay. I understand. Thank you.
In any case, after the class, you can perhaps ask me these specific questions. All right, so this is something that I solve all the time, but later when we talk about the energy concept, work concept, we can understand it better. But it is nice to talk about also in here. So we have these pulley systems, and the pulley systems, in that case, if we just adjust these kind of systems, it is possible to lift the object upward with a force much smaller than its weight. Right? You can think of it like that. So the object has a weight that's equal to mass times gravity. Whenever I use a scalar quantity, I'm going to use it as a scalar value, right? Just keep this in mind. And whenever I say that this, with a vector sign, I'm going to use it like that. So I would like to lift this object upward with a constant velocity. It doesn't matter if I lower it with constant velocity, the problem is going to be the same. Conservation of length method. There is no conservation of length. But in any case, I'm just going to say, yeah, I'm just going to solve these problems. But again, we are going to use the Newton's second law in here. What we do in each case is basically, I'm just going to consider this as an object. And sometimes I'm going to consider this as an object, for example, and that as an object. And then I consider all the forces that act on it. And I know that the acceleration of the object is 0, so they are moving with constant velocity in some direction. Whatever the velocity is, I don't care. And whatever the direction is, I don't care. Acceleration is 0, so the net force on it should be, on these objects should be 0. So in any case, let me just solve this problem for this one, because I don't have much time left in here. So let me say this is A, B, C, D. I'm going to solve it for part C. In here, I'm just going to say that this is 1/2 of mg. And in the second part, that's also equal to 1/2 of mg. In part D, I'm going to say that this is equal to 1/8 times mg. And there's also the force which is applied by the ceiling. So in this case, the force applied by the ceiling is upward, and that's equal to 1/2 of mg. In this case, force applied by the ceiling is 3/2 of mg. And it is upward. Yeah, probably I should have used with a different coloring in here. And in that case, this is 7/8 mg, right? But I'm just going to solve part C here. So in part C, how do I do this? I think I'm going to draw this again. Sorry about that. Okay, so as a result, I have these two objects in here. So that's object 2, that's object 1. In each case, we draw a free body diagram. A free body diagram means that I isolate these objects in some place in here. So this is the first object in here, and that's the second object. Isolate them and just draw their pictures, and then show all the forces that act on them. But before that, I need to use this fact that, for example, the tension in the strings in here, let me write T1 in here. This tension has the same value everywhere on the same string, but this is a different string, so therefore it's going to have a different tension. But again, on each part, the tension is going to be the same. So for the first object, we draw the free body diagram like this. We just consider all the forces that act on it from outside. So we have T1 applied on it from the left string, and T1 applied on it from the right string, and T2 applied on it from the bottom string. and there's no weight force. And for object 2, there are these, T2 is applied on it from left and right parts of the strings, and a weight force is applied on it. And in each case, we have like this, 2T1 minus T2 is equal to, mass is equal to 0, and the acceleration is equal to 0 for the pulley. Right? So at least for the pulley, since it's massless, the right-hand side is 0. For the second object, we have 2T2 minus mg, that's equal to, there's a mass in here, mass is non-zero, but the acceleration is 0. Right? It's moving at constant velocity. I don't care if it is moving upward or downward. There's no difference between them. So therefore, the right-hand side is equal to 0 for both cases, which means T2 is equal to 1/2 of mg, and T1 is equal to 1/2 of T2. So therefore, that's equal to 1/4 of the mg. That's basically in the corner, so I'm just going to write somewhere else actually. T1. And then there's a ceiling in here. The ceiling is something like this. There's a ceiling in here, right? That's the ceiling. Let's talk about this. I'm going to draw that part only, the ceiling. We can see that there are actually 2 strings attached to it, right? So there's this first string with tension T2 and the other string with tension T1. I think we don't have anything else, right? So therefore, I mean, you can compute the force applied on the ceiling, or you can compute the force applied by the ceiling on the lower object. So since I have said that what's the force applied by the ceiling, so we have like T1 on that string and T2 on that string. So these are the forces applied by the ceiling. That's basically the sum of these 2 forces. That's basically upward. So I know that the first one is 1/4 mg and the second one is 1/2 mg. So therefore, this is equal to 3/4 mg. All right, so I want to come back to the original picture in here. This place is already crowded, but let's just write this thing down. So there is a force applied by the ceiling, which is equal to 3/4 mg. There's a force applied by the hand. And what else? There's a force applied by the gravity, actually. But you can think of the combined effect of all of these. So as a result, let me also do it like that. All right. I'm just going to draw this picture again, but I'm going to draw it like that. There's a hand in here. Right, I'm not that good at drawing pictures. So I think I'm going to do it like that, right? All right. And then I have this mess in here. So in that case, you can think of the problem like that. You just consider this as an isolated object. Isolated object. This object is interacting with something outside. What is it interacting with? Well, it's interacting with the force of, with the hand. Hand applies a force on it, it's equal to the F. It's also interacting with the ceiling somehow. The ceiling applies a force on it. And it's also interacting with the Earth, with the whole Earth, actually, whole planet. The Earth is applying a force on it, so that's basically equal to mg. And as a result of that, I know that the acceleration of the object is equal to 0. The object in that case is complicated. There are pulleys as well, which are also doing this rotational motion as well. But as long as it's moving at constant velocity, and it's not going to change anything. So as a result, the net force, I can also write down the F net is equal to mass times acceleration in here. So for that case, I'm going to write the net force like that, minus mg in the upward direction, and the acceleration is still equal to 0. So you can check that the left-hand side is equal to 0, minus mg. Because the force applied by the hand is 1/4 mg. Force applied by the ceiling is 3/4 mg. And the force applied by the gravity is equal to mg. So somehow, the sum of all of these three forces should become equal to 0. Okay, so let me finish it in here. So the recording still continues, but if you have any questions in here, I can try to answer, right? So tomorrow I'm going to just keep solving these kind of problems, but I suggest that you also come to that class because I'm going to talk about how to deal with vectors. How do I write down these minus signs in here? If you are confused about these kind of things, I suggest that you actually watch that because I think that's going to be important. Because I know that a lot of people are just struggling with these kind of concepts actually. So let's clarify all of these. The problems are simple, but that's not the big issue. So we are just using these problems to illustrate the methods that we are using. Conservation of length method. I don't know what these conservation of length method is. There's a constraint in there. Yeah, the lengths of the strings are constant, but that's not a conservation. It's just a constant. We are going to talk about accelerated reference frames later, all right? We will talk about the accelerated reference frame. So we are going to give many examples, but I think in the there's actually a past exam questions file, PDF file on Oticlass. You can also find some examples in there. Not many, but there are some. But we will talk about accelerated reference frames. So that's one other thing that I actually deviate from the textbook because the textbook doesn't deal with these kind of things. But this is complicated, so as a result, we will talk about it later. Will there be a difference? Yes. I'm also going to place some videos of some problem solutions, offline videos that I'm going to prepare myself, right? So these are going to be different than the class videos, right? Is there any question that I missed? Yeah, if you have any other question, then you can ask me. So I'm going to stop the recording now, but I'm still in here.